Hello, welcome everyone to this special ICTS Distinguished Lecture. It's a great pleasure and privilege to have Professor Eisenbud here to deliver the ICTS Distinguished Lecture. Before I tell you a little bit by way of introduction to Professor Eisenbud, a word about the Distinguished Lecture series itself. This is something we have we have had a number of eminent scientists across the sciences in physics, mathematics, biology, and so on, computer science. To deliver a standalone lecture at a colloquium level, so accessible to a broadly sort of a scientifically mature audience. It's I think the first person in the series was Professor Ashok Sen, but we've had a number of luminaries, and just this year we had Marcelo Viana, Richard Karp, and I think Duncan Haldane at the beginning of the year, and so on. So it's a very rich tradition that we have, and so Professor Eisenbud is probably for most of the maths people in the audience needs no introduction. He is an eminent mathematician at the University of Berkeley, and also a very long time director of an institution which was one of our models, our templates for ICTS, namely the MSRI, the Mathematical Sciences Research Institute in Berkeley, up on the hill, one of the most scenically located institutions I have been to. Professor Eisenbud did his PhD in 1970 from the University of Chicago with mathematician Saunders MacLean, whom you might have heard of. He taught at Brandeis for many years before moving to Berkeley in 1997. I think he had a long stint as the director of MSRI, and then stepped down for some years, but came back again in 2012 or 13, I think, and is at the helm now. And MSRI does a number of different things apart from the programs. It's very heavily involved in outreach and the math circles in the US is in some sense anchored by MSRI. And while we started the math circles here, it was an inspiration to talk to some of the people involved in this at Berkeley. So we hope to play a sort of a similar role here. Professor Eisenbud's area of work is commutative algebra and related topics, in which he's made a number of contributions, a number of theorems, conjectures, and so on, bearing his name. And he has a number of awards and distinctions to his name, to his credit, with including the Leroy Steele Prize, and the Fellowship of the American Mathematical Society and the American Academy of Arts and Sciences, and so on. And he's produced a large number of very good students, I think over 30, I believe. And so let me welcome Professor Eisenbud to ICTS and this lecture, which will be a Blackboard lecture, and so I'm looking forward to it. So before the lecture, there is the small ceremony where we hand over a little memento. I'd like to invite our senior faculty associate, Professor Sujata Ramdore from University of UBC in Vancouver, who is also here. And this is a sandalwood Buddha that...
Good heavens.
Usually you get sandalwood elephants.
Sandalwood is a particular tree around here which has a fragrance.
Yes.
So, yeah.
Thank you. Thank you.
You can take it.
Oops. Thanks. Is the microphone on? And can you hear me clearly in the back? Even in the corner? Yes, good. Great. I was told that not everyone in this illustrious institution is an algebraic geometer. So I thought I would begin by giving a very short course in algebraic geometry. But first, let me say how pleased and impressed I've been by my little tour here. I just arrived last night from Mumbai, where I was at TIFR for a number of days. And really, this is a kind of paradise of a place to do mathematics and physics, it seems to me, and has tremendous potential for expansion and for training people and for hosting conferences. In fact, my thoughts have been about conferences I might propose in the future. So as with MSRI, people tend to come back once they've been there, and I hope that I will come back here too. So a little course in algebraic geometry first, but I wanted to outline what I'm going to do. Let's see, there must be white chalk as well as colored. It's a long walk down this blackboard, but not as long as some blackboards here, I gather. So first of all, algebraic geometry. Is this size legible back there? Is that okay? So I want to tell you the basics of intersection theory, because to do residual intersections without intersections would obviously be nonsense. Then I want to tell you something that you probably think you know, and maybe you do, which is what is a circle? Everybody know what a circle is? And alongside that, how many are tangent to 3 given circles? This is an easy thing to draw, so I invite you to draw it for yourself and know the answer. And then 3 problems which are really the motivating problems for residual intersection theory. First of all, the slightly harder problem of how many conics. Is this still big enough? Are tangent to 5 conics. I'll explain why 3 and 5 appear in these numbers. Is that still big enough? Yeah, good. And so that was a kind of curiosity of a problem in the middle of the 19th century. More significant was the development of the algebraic development of the Riemann-Roch theory. So let's say Riemann-Roch. For plane curves. Then, towards the end of the 19th century, people got tired of working with plane curves and began to think seriously about space curves, curves in 3 space. And a man named Helfin made a classification of low-degree curves in P3, and I want to describe that a little bit. Helfin, curves in 3 space. And then I promised something modern, so let's just say modern history here. This is a somewhat ambitious outline for 55 minutes, especially the first item. And so I may not get to it all, but you're welcome to ask me about any of it later on if you would like. So, algebraic geometry. First of all, why is geometry associated with algebra at all? And, you know, the basic theorem says that a polynomial of degree d has d roots. That's a connection between a set, a geometric thing, and an algebraic thing, the degree of a polynomial. And of course, it isn't true, even though we tell our students this in first approximation. First of all, over the real numbers, there might not be any roots at all. So you have to go to the complex numbers. And you can't really do that before about 1800 in the history of mathematics. So the first theorem is Gauss's theorem, the fundamental theorem of algebra. Polynomial of degree d has d complex roots. Now, even that isn't actually true because, or at least there are problems. First of all, it might have fewer, right? All the roots might be at one place. So you can't afford to count this set theoretically. You have to count with multiplicity. And of course, that's, until you make a definition of multiplicity, that's an empty statement. I see some roots and I count them with the multiplicity I like and I get d, so what? But in fact, the good definition of multiplicity in a very general situation has occupied algebraic geometry for probably 150 years, and now is pretty secure. But for roots of a polynomial, it's pretty obvious what to do. The other problem is, what is a polynomial of degree d? For example, ax plus b is a polynomial in x of degree 1 unless a is 0. What happened to its root when a became 0? Right? So if you think of this as a family of polynomials, you'd like a very uniform statement. Of course, the root is minus b over a. And as a becomes 0, this goes to infinity. So to make a really uniform statement, where it's really true that every polynomial of degree d has d roots, every non-zero polynomial of degree d, let's say, you should include infinity as a possible root. And then to make that systematic, you should work in projective space. So the right formula, the right place to do algebraic geometry is projective space over the complex numbers. And if you don't, how many people here know about projective space already? The others don't? Come on, you know about projective space. People are reluctant to raise their hands. I might call on you, right? So projective space is just the set of n plus 1 tuples, projective n space, tuples of complex numbers not all 0, modulo an equivalence relation, which is that a0 up to an, that's an n tuple, n plus 1 tuple, is equivalent to any scalar, let's say r times a0 up to r times an. If you like, you can think of that as rays through the origin in n plus 1 space. And if you draw a plane at unit distance from the origin, then most of the rays intersect that plane in points. So that plane was an n plane, and that's why this is an n-dimensional space. And then we've just completed it with an n minus 1 plane at infinity. For example, in the case of one variable, we completed it with 1 point at infinity. It's a little surprising at first that the point at plus infinity is the same as the point at minus infinity, but you have to do that to make these theorems true. And it's really just a circle modulo antipodal points. Here it's the sphere mod antipodal points. So it's a rather familiar thing, but it's the right home, or at least the easiest home, for algebraic geometry. It's the home in which theorems like this become true. So that's enough of that, but then we have a definition of degree, which is more general too. You can look at an algebraic set, a set defined by the vanishing of polynomials here, and because you're working modulo this equivalence relation, it doesn't really make sense to talk about the vanishing of an arbitrary polynomial because it might vanish here but not there. That's okay, though, if the polynomial is homogeneous, if every term has the same degree. So we talk about the vanishing of homogeneous polynomials, and we replace ax plus b with ax plus by. That's called homogenization, for example. And then we look at the pairs x, y, again, modulo that equivalence relation, and come to the same place we were before, not having done very much. So algebraic sets are defined by collections of homogeneous polynomials. Homogeneous polynomials I will habitually call homogeneous forms or just forms. A form of degree d means a polynomial which has every term of degree d. So algebraic set corresponds to collection of forms of some degree, different degrees perhaps, as we'll see. And there's a way to go back and forth. If you take an algebraic set, you can look at all the forms that vanish on it. If you look at the forms that vanish on it, a collection of forms, then look for the points where they simultaneously vanish. That's by definition an algebraic set. That's not too exciting. But let me do a slightly more interesting thing and talk about the topological classification of smooth curves in projective space, because it's a very nice algebraic version which is somehow a generalization of all this. So topological classification of, let's say, smooth curves. There's a perfectly good notion of singular curves. Curve just means, well, one-dimensional, but now we're over the complex numbers. So the set of complex numbers, which you might think of as two-dimensional, is one-dimensional from my point of view. And an equation, for example, a plane curve, that'll be something in complex projective plane defined by one equation. So as a real manifold, if it's a smooth curve, it would be two-dimensional, right? A Riemann surface. So these are our Riemann surfaces with their embedding in projective space. Pn is a remarkably simple classification. Just two numbers will do the job. First number is the degree of the curve. Well, the degree of the curve in the plane was just the degree of the equation that defined it, but we could define that geometrically as the number of points in which the curve meets a line. Because if you restrict the equation to the line, you get an equation on the line, still of degree d because it was homogeneous, and therefore it has d roots. So you see geometrically that a curve has degree d if it meets a line in the plane, if it meets a line in d points. And similarly, a curve in projective n space has degree d if it meets a hyperplane, the codimension 1 linear subspace defined by one polynomial equation in d points. So degree d, if and only if, let's say c, is of degree d if and only if c intersect h. Here's our first intersection, has d points. And of course, you know by now that this is a lie. It has to be a general plane, or you have to count with multiplicity, and you have to be careful that h didn't contain c, for example. But up to those caveats, this is a correct and accurate statement. There was a question I heard, a murmur of a question, or? Yes, so I will give you an example in a moment. When I say plane, everything is now going to be complex. Complex subspaces, complex things. Otherwise, now real algebra, it's not that real algebraic geometry isn't interesting, it's just that it's hard, much harder than complex algebraic geometry. The integers is even worse. Some people here think about that. But I'm going to stick with the complex numbers, and everything will be over the complex numbers. And this H is now a hyperplane. That just means codimension 1. So a line in the 2-plane, a plane in space, etc. D points. And the other number is the genus. Let's say G. What is the genus? Well, if you know about Riemann surfaces, of course, you know what the genus is. It's the number of holes in the donut, right? So if we look at the set of complex points of one of these curves, it looks like this, more or less. And of course, there's some geometry on the curve. It doesn't actually embed in free space where I'm drawing it, but never mind. It's number of hole. It's a sphere in genus 0. It's an ordinary torus in genus 1. It's a torus with G holes in genus G. So this is G equals 3. Now, this is supposed to be algebraic geometry, and I told you how to compute the degree algebraically. So I want to compute the genus algebraically too. And there's a remarkable fact that you get both numbers at once if you look at the number of forms of degree n, let's say, that vanish on the curve. And look at that for all n. So number of forms, it's called the postulation of the curve in the old days. The number of forms, by which I mean the dimension of the vector space of forms of degree n vanishing on C. So that number can be written in a rather simple way. First of all, the number of forms of degree n in projective space. If you think of the line, forms of degree n, there are n plus 1 coefficients, right? N plus 1 coefficients. That's P1, so n plus 1. If you just do a count of polynomials, you see that n in the plane, it's n plus 2, choose 2. In projective D space, it's n plus d, choose d, forms of degree n. So let's think of that as the main term, n plus, let's see, we're in degree d, nuts, I have too many numbers. Let's say I'm in projective cap R space. Okay, so, sorry?
What is the number of maximum G for a particular n?
For a particular n. So this should have been an R. So you can have curves of arbitrarily large genus. So for example, it's pretty easy to compute from what I'm about to say. The genus of a plane curve of degree d is d minus 1, choose 2. So it grows rapidly with d. But I'll come back to this question in a moment. So I write this as n, the degree of the forms, plus r, the dimension of the projective space, choose r. So if you write that out, that means n plus r times n minus 1 plus r, etc., down to 1 plus r, all divided by r factorial times, r factorial times n minus r factorial. So that's some number that just comes from combinatorics. I haven't put in the curve yet. So it's this number minus something, because the number of forms vanishing on the curve, of course, is smaller. And it turns out that the difference is of the form the degree of the curve times n plus 1 minus the genus of the curve. So it's a linear polynomial for large n. This is called the Hilbert function, or the Hilbert polynomial of the curve, and it's sort of the basic invariant. And the amazing thing is that it's a complete topological invariant of the situation. The curve, the topological invariant of the curve is just the genus. Together with the embedding, it's the genus and the degree. and they're all the same up to topology. There are, of course, lots and lots of different things up to analytic geometry or algebraic geometry. So that's what a curve looks like. And now an example is certainly overdue. Let's look at my favorite simple curve, which is the twisted cubic in P3. People in my seminar at Berkeley tease me that every lecture has to contain some reference to this curve, and it's nearly true. So the twisted cubic is an embedding of P1 in P3, sending a pair of homogeneous coordinates, x, y, let's say, to the 4-tuple, x to the 3, x to the x squared y, xy squared, and y to the 3. There are conveniently just 4 monomials of degree 3. You could do this for the rational normal curve. It's called in Pn just the same. Let's talk about this one. So this is an algebraic curve. It's isomorphic to P1, and P1 we know is rather simple. It's just a curve of genus 0, right? It's the Riemann sphere. So this has genus 0, so this image has genus 0 too. Let's say the image is the curve C in P3. So genus of C equals 0. How about the degree of C? Well, if you restrict, if you cut with a hyperplane, that means you put some linear equation on this, and think of it as an equation in x and y. Of course, it's an equation of degree 3, so it will have 3 roots, and so this is really a degree 3 curve, in other words, a cubic curve, it's called. So this is degree 3, and we could compute the Hilbert function too, but I won't take time to do that. More interesting is the equations, the forms that vanish on this curve, and they're rather easy to say too. If you look at these 4 things, that's really the result of multiplying x and y by the polynomials, the monomials of degree 2. So I can write a multiplication table, x, y, x squared, x, y squared, and I get, of course, x cubed, x squared y, xy squared, that's the first 3 of these, and then x squared y, notice the repeat, and xy squared, and then y cubed. So I think of this, if I think of these as the coordinates, let's call these z0, z1, z2, z3. I could write that matrix as z0, z1, z2, z1, z2, z3. And you can see that on the curve where the z's have these values, the 2 by 2 subdeterminants of this matrix will vanish. That's just the associativity of multiplication. X cubed times xy squared is x fourth y squared, and that's the same as x squared y times x squared y. So the 2 by 2 minors of this matrix vanish on the curve, and it's not hard to show that they're the whole ideal, a whole set. They generate the whole set of polynomials vanishing on the curve. So the ideal of C, which I'll write like that, is generated by the 2 by 2 minors of this matrix. The curve is dimension, the dimension of the forms of degree n, so it's this funny number where r is 3 minus the degree, which is 3. So 3 times n plus 1 minus 0. 3 times n plus 1. Right? 3n plus 1.
And these minors are the ones which generate the forms of degree.
They generate all the, they're all the forms of degree 2, but multiples of them give you all the forms that vanish on the curve altogether. It's the whole ideal of forms that vanish on the curve. multiples by forms. All right, maybe it's time to go to circles. Had enough of algebraic geometry. Oh, there's one other theorem I have to tell you, is Bézout's theorem. So Bézout's theorem is a generalization of Gauss' fundamental theorem, which you could think of as saying that a curve of degree d in the plane meets a line d times, right? That's the same as a form of degree d on the line, having d roots. But more generally, a curve of degree d meets a curve of degree e in d times e points in general. So here's a conic in the plane. A conic is a curve of degree 2. Here's another conic in the plane, and you can see 4 points. Of course, you might be nervous about moving one of these conics away, but that's just because the points become imaginary, become complex. So this is Bézout's theorem, and it works for any number of forms as long as they define a set of the right dimensions. So if I have 3 forms of different degrees in P3, then the number of points in which they meet is the product of their degrees. So that's Bézout's theorem. Let me just write Bézout next to this. All right, so let's do some geometry with this information. I promised you circles. Let's see, I guess I can start here again. So what is a circle? Circle, you know perfectly well what a circle is. It has a center, let's say AB. That's a point in the plane, and it has a radius, R. This is the center. So it's clear that there's a 3-dimensional family of circles, right? And if you homogenize the equation, so let's say the equation is x minus a squared plus y minus b squared equals r squared. If you homogenize this by adding a z where there isn't one, there's a z, there's a z, we better put a z squared here, then intersect that circle with the line at infinity. The line at infinity is z equals 0. Right? If I take z not 0, then I can divide by it and assume it's 1, and then I have my old equation of a circle. So that's the circle in the ordinary affine plane. Z equals 0 is where they go when they move out of the affine plane to infinity. So if I put z equals 0, I get x squared plus y squared equals 0. This is the intersection of, if this is C, then this is C intersected with the hyperplane at infinity. Well, the line at infinity in this case. And you can see there are 2 roots of this equation, namely 1 comma I, and, did I get it right? Yes, and I comma 1. And those are 2 points on the line at infinity. Well, a circle is a conic, something defined by a quadratic equation, which passes through these 2 points at infinity. That's what a circle really is in the complex projective plane. These are called the circular points at infinity for that reason in the old books. So that's what a circle is. And now, how about circles? How many circles are tangent to 3 given circles? So, of course, you could just draw 3 circles and try to draw the picture. It's not very hard, so I have 3 circles. And there's a circle passing around the outside of all of them, which is tangent to all of them. That's not a very round circle, but I'm sure you understand. There's one on the inside, and there's one on the outside of any one of these circles and on the inside of the other 2. So there are 8 ways to draw that. So there are 8 circles tangent to 3 given circles. Let's do that by Bézout's theorem. So circles form a projective 3 space. There are 3 parameters, as I told you, and you can just check that they're homogeneous in a moment. So circles, the set of circles equals P3. And I want to say, what is the condition for a circle to be tangent to a given circle? What's the degree of that form? And then I get to multiply the degrees, right? I'll have 3 conditions. I multiply 3 degrees and use Bezout's theorem. So, well, you can tell what the degree of the condition is in the following way. You have to look at a line in the space of circles and see how many times circles that correspond to points in that line are tangent to one circle, right? That'll give you the degree of the equation. So here's a family of circles, a 1-parameter family of circles. I'm just going to change the radius. Right? So how many circles in this family are tangent to a given circle? Well, you know, the circle is somewhere in here. It's over here. And finally, this collection of circles gets out that far and has a tangency. Whoops. And then a little further, it has another tangency, right? And then it'll never be tangent again. So the degree of the equation, we could write it out, of course, in coordinates, not very hard. The degree of the equation that specifies that a circle is tangent to a given circle is a degree 2 equation in the coefficients of the circle. Without any computation, we can see that. And so if you have 3 such equations of degree 2, then Bezout's theorem says you should multiply 2 times 2 times 2. You get 8, and we saw that that was right, right? So that's the kind of thing that people wanted to do with intersection in the middle of the 19th century. Projective geometry of curves in the plane was a big topic in the first half of the 19th century, and this was a common kind of question. Put some geometric condition on some kind of algebraic object and count. It's called enumerative geometry for that reason. And this is a pretty trivial example, but a more interesting example is this next one. How many conics are tangent to 5 given conics? And I promised Rajesh that at this point I would turn to him and say, how big do you think the number is? Sorry?
2 to the 5? No.
Well, so that's a good first approximation to a guess, because he says, well, maybe the condition of tangency is degree 2 again, and there are 5 conditions, so it should be 2 to the 5th. Actually, the equation of tangency is of degree 6. It happens. It's not very easy to draw in this case, to draw a family of conics tangent 6 times, a pencil of conics. Joe Harris and I spent a happy afternoon doing it one day with one of the geometry programs, but it's pretty hard. So these are 5 conditions of degree 6. So this is part 3. Conics, yes. What is the set of conics? A conic is just a form of degree 2. So what are the coefficients? How many coefficients does it have? That's all we're asking. Well, there's each of the squares, that's 3, and they're each of the products of 2 variables, that's another 3. So 6 terms, and we're in projective space. If you multiply all the coefficients, you get the same conic. If you multiply them all by the same number. So this is really a projective 5 space. So we have P5 is the set of conics in P2. And that's why I took 5 conditions, right? You would expect 5-dimensional space, 5 conditions, you get finitely many answers, and the number by Bezout should be 6 to the 5th, which happens to be 7776. I memorized that. Now that's the wrong answer, it turns out. Bezout doesn't work in this case. And the reason it doesn't work is very simple. It turns out that if you take a double line, something whose equation looks like linear form squared equals 0, then that algebraic condition, which is really just the condition for a double root at one point, the double line meets every conic with double roots. So that's being counted in this thing. And there's not a finite number of those, right? Every line in the plane has a double. How many lines in the plane are there? There's a 2-parameter family. That's linear form, so that's ax plus by. That's plus CZ. That's a 2-parameter projective space. So we have embedded in the set, which we described by these 5 sextic equations, 5 equations of degree 6, all vanish on the P2, which is embedded in P5 as the space of double lines. P2, sorry. So this is the double lines. And what we're really interested in is how many points other than the points of this image are there on which the 5 equations of degree 6 vanish. That's the form of a residual intersection. These 5 equations intersect in this space of double lines, which is called the Veronese surface, by the way. It's a lot like the twisted cubic over there. The space of double lines plus some points. How do you count the points? That's what the ancients wanted to do, is to count those points. And they pretty quickly realized that this was wrong, and they had to do something special. So this is a pretty hard problem in residual intersection theory, although it was solved already in the middle of the 19th century by Michel Charles. It took me a long time to learn how to pronounce Charles, but that's what it is, a Frenchman. And the year is 1852, I think. So I'm not going to reproduce that, but I will tell you the answer. The right answer is 3,264. So if you look on websites for Charles' theorem, you might find a picture or a set of pictures trying to draw the 3,264 conics. Turns out they come in conveniently packaged in sets of 100 or so, which you can draw. So this is an amusing thing. And you can make them all real, too, which is not obvious. Maybe some of them are pure imaginary, but you don't have to do that. So let's do a simpler example just to show what can be done. And I'm nearing the end of my time, so I'm going to go very lightly over these. But I think this is more fun than abstract nonsense. The twisted cubic, still on the blackboard, fortuitously, is defined by 3 polynomials of degree 2, as we saw. Now, if they were independent, if we could use Bezout, that would mean the twisted cubic had degree 8, 2 times 2 times 2. But that's not true. It's a cubic. It's degree 3. And that's because they're not independent enough. They don't intersect in points. If they intersected in points, there would be 8 points. They intersect in the twisted cubic. Suppose we took just 2 of them. What would we get? So intersection, it's a residual intersection of 2 conics, or 2 they're called quadrics in 4 variables. Again, an old name. That just means a polynomial of degree 2, form of degree 2, containing or vanishing on the twisted cubic So if we choose them generally enough so that they really intersect in something of degree 1, for example, if I choose this minor and this minor, then the intersection will be, by Bezout, a curve of degree 4. Well, 4 is 1 plus 3, so the rest of the intersection must be a curve of degree 1. So it's the twisted cubic plus a line. So this intersection of 2 quadrics containing the twisted cubic, that's equal to twisted cubic C union L, a line. And suppose I wanted to look at, so L is the residual intersection, right? C was the intersection that we were interested in, And we say that the residual intersection of two quadrics, of C in two quadrics, the intersection of two quadrics is a line, L. The residual intersection of the line in that intersection of two quadrics is C. It's a symmetric condition, very convenient. But now suppose we wanted to take, for example, two quadrics and a cubic. That's like the situation we had in Alphen, because then if you take two quadrics and a cubic, that is a form of degree 3 vanishing on the twisted cubic, then that will be something that still vanishes on the twisted cubic and maybe a little more. And suppose you wanted to count what's left over. So that's pretty easy. If I take one more form, something of degree 3 that vanishes on C, of course, if it's of degree 3, it will meet L in 3 points, right? So you might think the residual intersection was 3 points. But of course, L meets C, perhaps, in some way, in which case some of those points are the points of intersection. So to understand the residual intersection in this case, and this is similar to what happens for the Schall problem, you have to know something about how L and C intersect, right? If L is completely disjoint from C, then the residual is 3 points. If it meets C in 1 point, then the residual would be 2 points. If it meets C in 2 points, the residual is 1 point. And if L met C in 3 points, which turns out to be impossible, then it would be just no points. So the residual intersection, how do we determine whether C meets L in 1, 2, or 3, or no points? So the cases are sort of like this. Here's C and here's L, or here's C and here's L, or here's C and here's L. Right? Those are the 3 cases. And in this case, we have 3 residual points because the cubic meets L in 3 points. Here we have 2, because one of the 3 points is that one, which doesn't count. Here, the residual is 1, because those 2 points don't count. Now, here comes the genus to the rescue. Because this C union L is an intersection of just 2 quadrics, it's easy to compute the postulation, the Hilbert function. And it turns out from that the genus, the effective genus, is 1, and that these configurations have genus 0, or in fact, this one has genus -1 from this way of counting. So it has to be this configuration. And the extra information that we get from the genus computation says that the residual intersection is 1 point. So the residual is just 1 point in this case. 2 quadrics and a cubic. 2 quadrics and a cubic containing the twisted cubic. So that's the simplest, interesting residual intersection formula. And now I see my time is just about up, so I wanted to at least touch on these things. In the beginning of the 19th century, as I've said, people talked a lot about plane curves and about geometric properties of them. They knew about the genus, though they certainly didn't know about Riemann surfaces. But they saw that number coming up as an important invariant expressed in some other way. And they were very interested in the number of tangents satisfying a certain condition, all kinds of conditions like that. Then in about 1850, Riemann appeared on the scene and gave his wonderful inaugural lecture. And the whole view of what a curve was changed. He talked about it as coverings of the plane, not quite as clearly as that, but as ways of continuing a many-valued analytic function, branches of an analytic function. And he proved the Riemann-Roch theorem. And the algebraists couldn't do it. The people who worked with curves in the plane felt, this applies to our curves. Why can't we understand what it's about? So Brill and Noether undertook a long study to try to understand this. This is about 1882, I think, Brill and Noether. By the way, this is the father of Emmy Noether, Max Noether, studied Riemann-Roch in the plane, and they had to solve a residual intersection problem of a kind of worse kind. What happens in that study is you have two curves intersecting and a third curve which passes, whose intersection with the first curve is contained in the intersection with the second. So roughly speaking, you have a nice curve in the plane, C, maybe some complicated curve that meets C in some complicated way, like this, and a third curve that passes through that point of intersection. So you have to say how many times the first two curves meet at this, and what happens when you remove the intersection of the first curve with the third curve. There's no more curve there. Well, how are you going to do that? And it has to be symmetric again and things like that. This is possible, but it took quite a few years before people really understood why it was possible. I think Macaulay was the first to fully understand it in about 1930. But nevertheless, they worked out some theory that worked for the simplest cases and so on. They were very interested in that. So that's that topic. Then Halphen wanted to classify curves in P3. Curves in the plane, you know the degree, you know the genus, everything is simple. In P3, you can have different curves of degree D that have different genuses, different genera. And Halphen wanted to know what the pairs were, degree and genus. And he worked this out up to about degree 20, quite amazingly, by using this notion that I've talked about, by using residual intersections of curves. So he would take a curve that he understood, take two forms of some degrees that vanished on it, look at the residual curve, and from the first curve, he could deduce the properties of the second curve. And so that really was the key technique that allowed him to do that. This theory sort of bubbled on through the 20th century, and people jumped from curves in the plane and curves in three space to varieties of any sort in any kind of projective space, or even more fully. It became part of commutative algebra. Gorenstein rings turned out to be just the tool to use. There's a famous paper of Peskin and Spiro in which they do this all in the context of Gorenstein local rings, such as the local ring you get from the polynomial ring by localizing at the origin. And then Artin and Nagata wanted to go beyond the case that Peskin-Spiro did, which was like Halphen's case, where you take a variety of degree D, dimension n, and you get another variety of dimension n. That's called linkage. So Artin and Nagata, two very famous algebraists, wanted to go beyond that, and they proved the main theorem about the linkage case in this more general setting, and they made a mistake. The mistake was found by Craig Hunicke a few years later, who produced a counterexample and a kind of fix. And that's a theory which has now been pursued a great deal in modern times. Maybe the champion person in that is Bernd Ulrich, and he and I have worked together as well. So there are lots of questions remaining about the residual intersection case. Let me state just one for the case, for this case of conics in the plane, which was left open by the ancients. When you take this residual and you get a set of points, there's actually a natural set of polynomials associated to that residuation process. And the question was left over, are those polynomials all the polynomials that vanish on that set of points or not, just some of them? And that's fairly recently been settled by Hunicke and Ulrich and others, and the answer is yes, they are. But that is the beginning of a long and technical modern theory of this subject, which is still being refined and pursued. So thanks for your attention, and I hope you know what residual intersections are now.
Thank you very much. Questions? 1 second.
Number 4, Yemeni and Rosman. has it any relation with the argument principle of the complex variable? Principle of the complex variable to extract the winding number?
So I'm not quite sure what you mean. I mean, it is a theorem in complex variables theory, yes. Riemann did it as a theory of analytic continuation of functions of a complex variable.
It's called the argument principle, sir.
Sorry?
The argument
He's,
principle?
I think, talking
that's a
about
little
the
bit-
winding number.
the winding number.
But I don't know if this is related to the winding.
Topology.
I don't think it's directly related.
Okay.
But when you have this covering of the Riemann surface over the punctured plane, you have monodromy groups around each point of the puncture, right? And that's there the winding number becomes important in homotopy theory. And if you put all those ramification groups together, you can deduce the genus of the cover. Between the cover has a degree and a lot of ramification that gives you the genus in a different way. But it doesn't quite yield Riemann-Roch, I think.
It's like the Riemann-Hurwitz formula.
Yeah,
type,
that's right. That's right. Yeah.
More questions? So normally the Riemann-Roch, you at least the way I encounter it and so on, in terms of you look at it in an analytic fashion in terms of some index or something. So is there a way to connect the analytic property to this algebraic?
So Riemann-Roch is an attempt to compute the number of sections of a sheaf, right, at its base. And it's a kind of analytic formula for that in terms of a fixed number, the degree minus genus plus 1, and a number which is complementary to the number one wants, which is the number of sections vanishing, the sections of the canonical sheaf vanishing on a set of points, which is the divisor associated to your sheaf. So if you like, the way I would typically express Riemann-Roch is that the dimension of the global sections, analytic global sections of a line bundle L, this is a primitive form of Riemann-Roch, maybe compared to the index form you're thinking of, minus the number of sections of the canonical sheaf tensored with L inverse. So holomorphic differentials vanishing on a divisor associated to L is equal to the degree of L minus the genus of the curve plus 1. So that's the Riemann-Roch formula in the form that we teach it now to beginning algebraic geometry students. Of course, there are many other forms which have to do with elliptic operators and things like that, and that's perhaps what you're thinking of. But they're all generalizations of this notion of counting the number of sections of something or counting the dimension of the kernel of an operator, something like that, in terms of some kind of Euler characteristic, which is maybe computed by an intersection formula. So
but the left-hand side, what is the geometric?
So geometrically, we're looking at.
I mean, in terms of plane curves, is there a way?
So there's a notion, if you have a plane curve and a set of points on it, then there's a notion of linear equivalence of those points. So if there's a rational function vanishing on these points with poles at some other points, then you say that this is equivalent, linearly equivalent to that. So zeros here, poles here are linearly equivalent. So there's a whole family of points linearly equivalent to these. And this is the dimension of that family. This is the dimension of the family of points that you get by taking a differential form and looking at its zeros and subtracting one of these equivalent sets from that set of zeros, a residual intersection, getting yet a different set of points and looking at how much they move in linear equivalence. So that's the geometric way of saying it. There's maybe there are a lot of different ways of saying it. For a curve of genus, at least two, most of the time, the global sections of this sheaf of differentials gives an embedding of the curve into space, and this is a formula for the failure of a given set of points to be linearly equivalent and linearly independent in that embedding. So there are many different geometric forms of this, but it's a very fundamental result that permeates the theory of curves and then was generalized to surfaces and higher dimensional manifolds. There's the Hirzebruch Riemann-Roch theorem, then there's, of course, a T.S. Singer, and on it goes into the world. A message.
And no, we live stream this, so sometimes,
yes.
so people sometimes ask questions.
Good.
So yeah, so this is sort of, so there's someone called Siddharth Acharya who asks, do residual intersections have applications in Gromov-Witten invariant theory as well?
Absolutely. So the answer to that is yes. This is, if I had a fourth topic there, it was going to be Gromov-Witten. So you look at the space of maps from curves of genus something or other, G, into a variety or into an analytic manifold such that the image lives in a certain homology class, that's the equivalent of degree in the general sense, and satisfies some more conditions, just enough to make the count finite. Passes through a certain set of points or has some relation to some submanifold there. And then it turns out that counting that set is a residual intersection problem, because when you look at the algebraic varieties involved, they turn out to have the wrong dimension, just as the intersection of these 5 sextic equations had the wrong dimension. And so what you really are looking at is some kind of residual intersection. And there's a very elaborated theory of when you do intersection theory in a space that isn't a smooth space, it means that you multiply in cohomology and then cap with a fundamental class, except that these spaces don't have fundamental classes of the right dimension. So there's a virtual fundamental class, and you get into this kind of residual intersection problem. Anyway, that's roughly the relation with Gromov-Witten.
In fact, it's interesting. The next question is from an undergraduate student, Shahbaz Khan from ISI Bangalore. So, so I guess it was too far to make the trip here, but he's watching it online, and he asks, at some point you discussed the case of residual intersection of 2 quadrics and said that with 3 residual points, the case with 3 residual points has genus -1. So can you explain what a negative genus means?
So genus is defined in that setting by the formula which I think I've erased.
Hilbert formula.
Yeah. But there was a formula for the number of forms in projective space minus a certain linear function. And the genus is, you compute the number of forms vanishing on the object you're interested in and just take the coefficients of that linear function as the definition of degree in genus. And it comes out to be -1. What can you do? So it's not very hard to compute the number of forms vanishing on a twisted cubic and a disjoint line. By the way, that was the residual intersection of 2 quadrics and a cubic in the twisted cubic.
This last...
Yeah, this last picture. If it were like this, if the 2 quadrics had this as intersection, then we would have had 3 points, but they don't. They have this as intersection. The extra line you get meets the twisted cubic in 2 points. And one can see that even from this example. If you set Z1 and Z2 equal to 0 in this, so let's see, if we cross out all the Z1s and Z2s, then we get a product of 2 variables. So of course that's degree 2, right? So in this case, the twisted cubic meets that line in 2 points defined by the product of those 2 coordinates. algebraically. Sujata has a question.
Yeah, but just one small follow-up from the same person.
Okay.
He's actually not in Bangalore right now, so he clarifies. But he then asks, can you give some reading recommendations aimed at beginners in the field?
So I think a nice book to read is the book of Cox, Little, and O'Shea, which connects polynomials and algebraic varieties.
There's ideals, varieties,
and algorithms, I guess it's called, yes. That's a nice book. And there's also a very famous and influential book, an old book, by Elbert Walker on plane algebraic curves, which does a lot of this theory too.
Okay.
So since you're a McLean student, and since you're also in commutative algebra, so what was so uncanny about commutative algebra and homological algebra sort of walking the same path? That's the first question. Second is there a homological algebraic interpretation of residual intersections?
Okay. Yes is the answer to the second question, but let's talk for a moment about how commutative algebra came to be mated with homological algebra. Homological algebra is really developed by Eilenberg and MacLean early on, but there were two big theorems in commutative algebra that were sort of waiting around to be proved. So Krull was the one who defined a regular local ring. So a local ring, something like a power series ring in n variables, and the fact that it has n variables and dimension n makes it a regular local ring. And in general, if local ring has a maximal ideal and its number of generators, if that's equal to the dimension, that's called a regular local ring. This is fundamental in geometry. Zariski, later, actually, than Krull, pointed out that this was what a smooth point on a variety was, or a non-singular point. He called it a simple point. But Krull was there first. The algebraists came first, I like to emphasize, and recognize this as a fundamental object in algebra. So Krull could prove that if you had a ring which was a localization of a polynomial ring, that's always a regular local ring, then, well, that's what he proved. It's again a localization of a polynomial ring or something of finite type more generally. If the ring is regular, then the localization is regular. There's no connection that's obvious, right? You have a maximal ideal here. When you localize at some prime, it goes away. How do you connect the two? And so they wanted to prove in general that the localization of a regular ring was regular. And that was only proved by what I would have said was representation theory, though you could call it homological algebra. It's the theorem of Auslander, Buxbaum, and Sayre that regular local rings are characterized by the fact that every module has a finite free resolution. And that obviously localizes and therefore proves the theorem. And then very shortly afterwards, Auslander and Buxbaum proved another one of these sort of conjectures that were hanging around that had been proved for the simplest case, the geometric case, and showed that regular local rings are unique factorization, have unique factorization into irreducible elements. So those two theorems were so impressive to everyone. Sayre wrote a book about them, right? And other related things that that the two subjects somehow got together at that point, and I think they've never left each other afterwards. Homological interpretation of this. What is a residual intersection really from the point of view of algebra? I didn't come clean, I'm afraid, about that. So, so an algebraic variety V in some projective space maybe corresponds to an ideal inside the polynomial ring, C of x naught up to xn, namely the ideal of the set of all forms vanishing on V. And if you have something defined by a couple of equations vanishing on V, let's say F1 up to F codimension inside this ideal, then the residual to V, so the residual of V in F1 equals dot, dot, dot equals FC equals 0, this is another algebraic set, is defined algebraically by the ideal quotient F1 up to Fc colon I. This means the set of all forms which, when multiplied by everything in I, anything in I, are in the ideal generated by F1 up to Fc. So this is the fundamental algebraic construction. And now, if you want this to behave well, for example, if you want, suppose I is Cohen-Macaulay and you want this residual to be Cohen-Macaulay again in general, then you need lots of homological conditions on I, it turns out. The first one that was known was Hunicke's strong Cohen-Macaulayness, which means if you take the Cazul complex on generators of I, then every homology group is Cohen-Macaulay module. But there's a whole litany of more and more technical and more general conditions under which such things are true. So homological algebra plays a very deep role in this theory, and in a very technical way, which I didn't want to get into. Yeah.
Pranav,
I guess this is just a natural follow-up question to the previous one. Has derived algebraic geometry played any role in the modern development of?
Sorry, I couldn't
Has
understand.
derived algebraic geometry played a role in the sort of modern development of?
In this theory.
Yeah, in this theory.
So not yet, I guess, is the answer. So derived algebraic geometry means you replace rings by simplicial rings or complexes of some kind and work in that framework. And it makes some things much simpler. It makes some things smooth looking that weren't smooth before. And so it broadens the field of endeavor quite a bit. But I have not seen anything about this in that circumstance. Interesting idea. Why not? Yeah.
okay, if there are no questions, remote questions or any. Yeah. Okay, from the person who asked about Gromov-Witten theory, Siddhartha Acharya, can we obtain a surface of negative genus by identifying sides of a polyhedron like the Poincare polyhedron theorem?
I don't know the answer to that question. In general, something irreducible always has positive genus. A curve which is irreducible and reduced has positive genus. The reason that this thing was allowed to have negative genus was that the line had sort of floated away. So, but if you have an irreducible reduced curve, it's always of positive genus. And if you take a polygon in the plane and identify sides to get a Riemann surface, then that's always a positive genus, certainly. I'm not sure whether he meant surface in the sense of Riemann surface or surface in the algebraic surface sense, but probably Riemann surface from that, from the sound of it. Yeah. No, this is the tame part of this theory behaves as one would think, counting holes in a torus.
Okay, no further questions. Then let's thank Professor Eisenbud again.
Good.
In